Hey guys, welcome. Yeah, so I introduced the delta-epsilon limit definition in my Advanced Calculus 2 video series. There, starting with example 0, I give you a total of 5 examples, or maybe 6, I don't know, but yeah, definitely at least 5. And so if you need an introduction to the delta-epsilon limit definition, then check out those videos. The first of those videos is example 0, which, as with all my example 0s, discusses the idea thoroughly. So yeah, if you really want to understand the delta-epsilon limit definition, watch example 0 on the delta-epsilon limit definition in my Advanced Calculus 2 video series, yeah? And as I said, there are more examples there. Cool. But yeah, here, an analysis, we'll look at our first advanced example and proving this limit here. Okay, now, while I will not repeat myself from the things I taught you in Calc 2, here's a quick recap of what the delta-epsilon limit definition said. It said that for every epsilon greater than 0, there exists a delta greater than 0 such that for all x, whenever the absolute value of x minus a is less than delta, it immediately follows that the absolute value of f of x minus L is less than epsilon. If this is true, then we can say that the limit as x goes to a of f of x is equal to L. Yeah? Okay, so again, I already explained it in example 0 in my Calculus 2 video series. Yeah, example 0 of the delta-epsilon limit definition, of course. But yeah, quickly, let's get a visual for what we're doing. So here we're considering f of x equals x cubed. That's a function, and we know what that looks like. It looks like this. Yeah? Now let's say that the point A along the x-axis is there. Okay, so this limit definition is an epsilon challenge. What that means is that, as it says, for every epsilon greater than 0, so someone prescribes you an epsilon, so say like epsilon is 0.01, what we have to do is, for every epsilon prescribed, since we're saying that the limit as x goes to a of the function f is L, there's an epsilon neighborhood now by the prescribed epsilon, and what we have to do is find a delta so that a delta neighborhood about the point A along x, so this is like delta amount on either side of A, and this is an epsilon amount on either side of L. But yeah, you're given an epsilon, and the challenge is, and this is why it's an epsilon challenge, the challenge is to find a delta so that the delta neighborhood about A will have all x's being mapped by the function f onto the epsilon neighborhood about L. If you could do that, no matter how small the epsilon neighborhood originally prescribed may be, then, that is, if you continue to find a smaller and smaller delta neighborhood about A so that all of those x's are mapped onto your continually smaller and smaller epsilon neighborhoods about L, then if that challenge is met for all epsilon greater than 0, it must mean that the limit is x goes to a of your function is in fact L. Yeah? Okay, so that should have done you well. But yeah, a lot of those introductory videos concern the mechanics of what we're about to do, right? So the mechanics of the delta-epsilon limit definition proofs, not so much the concept. The concept is an example 0, and I just like gave you a little, additional reinforcement, if you want to call it that. Okay, so let's get to the mechanics. So the mechanics is, well, here, since a is any random x value, we must start with x minus a is less than delta, will automatically imply f of x here is x cubed. So we'll automatically imply that x cubed minus L is a cubed is less than epsilon. This is what we want to show, that for every epsilon greater than 0, blah, blah, blah. So this is like, the hypothesis, but the meat of the argument is right here. And so what we want to show is whenever this is true, that this will automatically follow. And so here in the mechanics, what I said in the introductory videos in Calc 2 will still be valid, which is start with this right hand side and start manipulating it, and that's how you're going to create the delta epsilon relationship that's generic, and we'll say, hey, yeah, for every epsilon use this formula for delta and it will work every single time, or use this expression more than formula. Okay, cool. And the name of the game is, like, in manipulating this guy, try to get x minus a, an absolute value, to show up in this part. Okay, so now we know that by difference of cubes factoring, that like v cubed minus u cubed, it's better I start with u, right? U cubed minus v cubed is u minus v, u squared, plus uv plus v squared. Right, that's true. Okay, so then that means that the absolute value of x cubed minus a cubed is equal to the absolute value of x minus a, I'm just using this here, times x squared plus ax plus a squared. Yeah, okay. All right. And so since we want this to be less than epsilon, we want this to be less than epsilon. But wait, if we just focus on this part right here, we see that next we could write that this here is the same as the absolute value of x minus a times the absolute value of x squared plus ax plus a squared. Right? This here is the same as this absolute value expression right there. That's just absolute value rules. So we'll say that this is less than epsilon. Remember, what I said was the name of the game is to get this guy to show up, and here it is. So then we see that if we divide both sides by this, we're going to get that x minus a is less than epsilon over the absolute value of x squared plus ax plus a squared. Yeah? Okay, cool. Okay, so then we should say that delta should equal epsilon divided by this here, this absolute value expression. And then we have created the delta epsilon relationship that we wanted. Cool. So we're basically done for like the main part. The rest of what we have to do now is make this relationship between delta and epsilon free of x. Yeah? So right now we're saying we should let delta equal epsilon divided by this here, right? So we have a good start, but now let's work with this and make it free of x. That way the relationship between delta and epsilon is free of x. How do we do that? Well, first, notice that the absolute value of x squared plus ax plus a squared is lesser or equal to the absolute value of x squared plus the absolute value of ax plus the absolute value of a squared. And this here is true by a double application of the triangle inequality theorem, and I have a video stating and proving the triangle inequality theorem, so check that out. But it's, yeah, a useful theorem in analysis, and here it is, it's useful here. Yeah, so a double application of the triangle inequality theorem gets us this. Next, we can say then that this here is lesser or equal to absolute value of x squared plus absolute value of a, absolute value of x, plus absolute value of a squared. And this is just applying absolute value rules. Now, in those 5 videos in Calculus 2 where I introduced the delta epsilon limit definition, I show you that that the absolute value of x minus the absolute value of a is less or equal to the absolute value of x minus a. Okay, so this is true. In addition, in a lot of these delta epsilon limit proofs, you want to put a cap on the absolute value of x minus a. And this makes sense because, well, as you saw when I was drawing my delta neighborhood about a, visually I didn't pick a very large interval, and there's no need, right? because ultimately you're going to challenge me by picking smaller and smaller epsilons, and so my deltas need to be sufficiently small, right? And so then considering an interval about a, and therefore a delta that is somewhat small, makes sense. Any positive number for delta would work, but 1 is sufficiently small. So using that for delta, let's here say that there's a cap on the absolute value of x minus a, and that it's less than 1. Fine. Then that means that this statement can then be written as absolute value of x minus absolute value of a is less than 1, right? That's because this here, absolute value of x minus a, is less than 1. And then next, adding absolute value of a to both sides of this last inequality, we can write that the absolute value of x is less than the absolute value of a plus 1. Yeah? Okay, cool. And so remember, we've put a cap on the absolute value of x minus a. It's less than 1, right? And these are transitional statements. And I need the space, so let me erase. All right. So then where can we go with this? Well, you see I have this here, all right? And so absolute value of x, that is, and I could replace it with this. And by replacing it, then I could write this statement, which is that this here is strictly less than now, because, well, absolute value of x is strictly less than this. It's strictly less than absolute value of a plus 1 squared plus absolute value of a times absolute value of a plus 1. Again, here I'm replacing absolute value of x with this right-hand side, and even more secure in keeping that then. And then, of course, plus absolute value of a squared at the end. Got it. Now, this is a situation where we have like 4 is less than 5, if we want to simplify, like thinking about this. Well then, epsilon over 4 should be greater than epsilon over 5, right? So what I'm saying is that epsilon over this, which is what we have here, will be bigger than epsilon over this. So this is what I'm saying. Let me write it actually. Epsilon over absolute value of x squared plus ax plus a squared is going to be bigger than epsilon over this expression. I wish I could just copy and paste it. Okay, and that is right? Okay, cool. So earlier we were going to pick delta to equal this, and that would have satisfied, right? That would have satisfied our requirements. So if we pick delta to be this, it's even smaller than this, so we're doing better. So there we are, we're done. So what we should do is, well, I don't need any of this anymore. So what we should do is let delta equal, remember we've put a cap on the absolute value of x minus a to be less than 1. So let delta equal the minimum of 1 or epsilon over this. Yeah, again, since letting delta equal epsilon over this here would have sufficed, picking something smaller for delta will be even better, right? Okay, and there we are. Yeah, okay, cool. Yeah, I don't think I need to say more. I hope you enjoyed this, and if you have questions, yeah, ask in the comment section. Keep watching. Take care.